This video pertains to section 7.1, chi-square intervals for the true population variance and true population standard deviation. As always, I have rounding rules. This time we're going to follow number 7, confidence intervals for true population variance and standard deviation. If it's raw data that we're dealing with, then you round your final answers of the confidence interval to one more decimal place than the number of decimal places in the original raw data values x. If the data is not raw, then you round your final answers, the lower number and the upper number, to the same number of places as the given sample variance or sample standard deviation. There is one exception to both of these rules, and that would be money. Problems involving money say to round to 2 decimal places accurately, and that's the lower number and the upper number. The other thing that I wanted to show you would be this new chi-square table. This is called the famous chi-square table. Once again, you will need degrees of freedom. Degrees of freedom will be your sample size minus 1. The word problem gives you sample size, so go to row sample size minus 1. These values, 0.995, 0.99, all the way to 0.005 are areas. And those are areas strictly above the chi-square value on the axis. All of these are chi-square values, and they are given to 3 places, and they're all positive. At the bottom of the table, the chi-square table, you have your chi-square axis. This chi-square value on the axis is unknown, but the area at the very top of the table would be the area above it. And this is how the table works. The areas at the top are the areas strictly above those chi-square values that we're looking for on the axis. And that is how the chi-square table works. I will teach you how to find this table. It's necessary in order to calculate chi-square intervals for the true population variance and true population standard deviation. So I will refer to this table very often throughout the lecture notes. The next page of the lecture notes pertains to the properties of the new chi-square distribution. Again, these are variance, confidence intervals for true population variance and true population standard deviation, sigma squared and sigma. We may never know the true population variance or true population standard deviation, but we can be a certain degree confident that those values fall between 2 numbers. The properties of this new distribution called the chi-square distribution, the symbol is chi squared. I know it looks like a capital X, but it is the Greek letter chi squared. And the chi is pronounced as ki, so that's why I say chi squared. Some students say chi, but it's supposed to be chi. It is similar to the student t distribution, the t variable with the student t distribution. It is not just one curve, it's a family of curves based upon degrees of freedom, sample size minus 1. A chi-square variable on the chi-square axis is always positive, it's never negative. You know, you could have negative z-scores, and you can actually have negative t. We haven't really talked about this, but once we cover hypothesis testing and we explore the student t distribution a little bit more, you'll see that those values from the t table, those t values on the t-axis can also be negative. But here with the chi-square distribution, the variables on the axis are always positive, so they cannot be negative. All chi-square distributions are skewed to the right, so they're positively skewed or skewed to the right, right skewed. The area under each chi-square distribution is 1 or 100%. At about 100 degrees of freedom, and that means your sample size was, 101, the chi-square distribution becomes more and more symmetrical or normal. Two different values are used with these confidence intervals because the distribution is not symmetrical, and it's called chi-square from the left and chi-square from the right. Capital L means left, capital R means right. The picture for a general chi-square distribution looks like this. You have your chi-square axis, and you can see all of these are positively skewed or right skewed. And this value here starts at 0. And that's another reason why I would say that the chi-square values on the axis are positive. So it goes from 0 to positive infinity. The degrees of freedom are increasing from 1 to 4 to 9 to 15. And you can see as degrees of freedom are increasing, sample size is increasing. So at about 100 degrees of freedom, the chi-square distribution becomes more and more symmetrical or normal. Again, here are the rounding rules, and I've typed those on the rounding rule sheet, so I will not have to read those again, but those are the rounding rules. And here are the formulas. For the true variance sigma squared, the lower number is sample size minus 1 times s squared, which is sample variance, divided by chi-square from the right, and I'll show you how to find that in the chi-square table. The upper number is m minus 1 times s squared divided by chi-square from the left, and I'll show you how to find that value from the table. For confidence intervals for true standard deviation, sigma's in the middle. The only difference between this formula and this formula, this is for true variance, this is for true standard deviation, but we take the square root of the lower and the upper. The TI-84 will not find these confidence intervals for you, the TI-84 and the TI-83. The TI-83-84 will be useful if we have to calculate sample variance from raw data. And that will be the only time that the TI-83-84 is going to be useful. I would like for us to look at the problems. And these are the problems discussed in the lecture notes. First problem just deals with using the famous chi-square table and how to find those chi-square from the right values and those chi-square from the left values. It says for a chi-square distribution, find the two chi-square values for a 90% confidence interval when the sample size is 25, and I have a space for those. You only need to know your degree of confidence and your sample size. And then we have a problem that says find the 90% confidence interval for true population variance and true population standard deviation of the ages of seniors at Oak Park College if a sample of 24 students had a standard deviation of 2.3 years. Assume the variable age is normal. And the last problem is raw data. A new car dealer is leasing various brand new models for the monthly rates in dollars listed below. Estimate true population standard deviation in leasing rates with 90% confidence. Assume the variable is normally distributed. Here we are going to have to find the sample variance s squared from the raw data. So I just want to start with number 1 and go kind of slow here with showing you how to use the famous chi-square table. Problem number 1 again says find the two chi-square values for a 90% confidence interval when the sample size is 25, and these are the values. Chi-square from the right is 36.415 and chi-square from the left is 13.845. Excuse me, 13.848. These are the answers. Now I have the steps here in the lecture notes on how to find those values, but I am going to show you on the document camera. That's the purpose of the integrity video. We know that it's 90% confidence for the true variance and the true standard deviation when n is equal to 25. Step number 1 would be to find degrees of freedom. You would go to row 24. Chi-square table, row 24. Number 2, I highly recommend that you draw a picture of this chi-square distribution. You have your chi-square axis, and it goes from 0 to positive infinity. And just a general chi-square curve here. It is positively skewed or right skewed, as you can see, and they do start at 0. What you're going to be finding every time is a value on the axis called chi-square from the left and chi-square from the right. Both of them are positive because the axis does begin at 0. Chi-square from the left will be smaller than chi-square from the right. You will shade the right tail and you will shade the left tail. And that's a great picture to have. Going back to the chi-square table, remember these areas above is called alpha. These are the areas above the unknown chi-square value on the axis. Again, the picture is here. It says area alpha. Those are the areas up at the top. Would be the area above this unknown chi-square value. That means that we know we go to row 24. We have to figure out what this area is above chi-square from the right, and we have to figure out what this area is above chi-square from the left. Those are the areas that we look up in the chi-square table. Those are the columns that we go to. We go to row 24 regardless, but the area above these unknown chi-square values will be the columns that we need to go to. With the rest of the picture, I would say that your 90% degree of confidence is going to be tell you a lot of information. What you have is for this unshaded area, it's 90% or 0.90. Remember that the total area under the curve is 1 or 100%. That must mean that this area is 5% and this area is 5%. And that's 0.05 and 0.05. If you were to add up all of those areas, 0.05, 0.90, and 0.05, you would get a total area of 1 or 100%. So the 90% is the given degree of confidence, and it's that unshaded area in between the two chi-square values that I'm trying to find. The area above chi-square from the right is 0.05. The area above chi-square from the left is 0.95. 0.90 plus 0.05 is 0.95. And that's how the chi-square table works. You have to look up the area above the unknown chi-square value. We're trying to find chi-square from the right. The area above it is 5%. And we're trying to find chi-square from the left. The area above it is 95%, which includes this area and this area. So I will go to column 0.05 and row 24, column 0.95 and row 24 to find those two chi-square values. Before I do that, there is another way to look at this. Alpha that I showed you here, and again these are the areas above the unknown chi-square value according to the picture here. There are a couple of different steps you could go through, and I'll show you those in just a moment, but let me show you the table. Go to row 24 because our sample size happened to be 25, and then for chi-square from the right we go to 0.05. your two fingers meet at 36.415. That's going to be your chi-square from the right, and it's positive. Then you go to row 24 and column 95%. 0.95 is the area above chi-square from the left, and that number is 13.848. And I'll write those down. So row 24, column 0.05, that's the area above chi-square from the right. So the value on the axis, chi-square from the right, is 36.415. And then chi-square from the left, the area above it's 95%. And then row 24, the chi-square from the left on the axis is 13.848. And I'll write these down in the picture here. Now we actually know this number, and this number is 13.848, and this number is 36.415 from the table. You could also say that chi-square from the left is 13.848, and chi-square from the right on the axis is 36.415. As a quick review, to know which row you go to degrees of freedom, sample size -1. That's simple. To know the columns that you go to, the unshaded area is the degree of confidence, 90%. That leaves 10% divided between the two tails, so each tail is 5%. Start at 0 on the axis and go out to positive infinity, and these are chi-square values. The area above the unknown chi-square from the right is 5%, and the area above the unknown chi-square from the left is 95%. Those are the columns that you go to. So first I'll go to column 0.05, and then I'll go to column 0.95, and both of those row 24. And then we know our two values on our axis, chi-square from the left and chi-square from the right. And that completes problem number 1 in the lecture notes, but I do want to show you this. I have in the lecture notes that if you don't want to draw the picture, there are steps. If you know your sample size is 25 and it's 90% confident, first step is 25 minus 1, which is row 24. To find chi-square from the right, you will say 1 minus your 90%, which is the total of 10% in the two tails, if you remember. That's actually equal to something called alpha. Alpha divided by 2 would be the area in each tail, the left tail and the right tail. If you remember, each tail had 5%. So for chi-square from the right, you will go to the column that says 5%. So 1 minus degree of confidence is the area that's in the two tails together. That area divided by 2 is the area in each tail separately. And then that's the column you go to for chi-square from the right. Chi-square from the left would be the column that you go to, would be the total area under the curve minus the area of 0.05, which is the area in the left tail, is 5%, so that means the area above chi-square from the left is 95%. These are the steps without the picture, and I also have a little insert from the table here. Row 24, column 0.05. This was alpha over 2, and this is 1 minus alpha over 2. That's the procedure. Alpha over 2, 1 minus alpha over 2. And alpha is 1 minus your degree of confidence. You can follow these steps every time if you wish to find chi-square from the right and left. or you could draw the picture. So 1 minus given degree of confidence is 10%, and that's alpha, that's the area in both tails together. 5% and 5% is 10%. So alpha is 10%. Alpha over 2 is going to be 5%, and that's the area in each tail. So 5% is alpha over 2. And then chi-square from the left, the area above it is 1 minus the 5% that's below it. Here's chi-square from the left. 5% is below it, so the area above it is 95%. You could also do this. 1 minus alpha is going to be 90. If you remember, 1 minus the 0.90 is 10%, which is alpha. It is also true that 1 minus alpha, which is 1 minus my 10%, is my 90%, my degree of confidence. So this unshaded area is the given degree of confidence, also 1 minus alpha. And alpha is 1 minus the degree of confidence. That's how the two are related. And then each tail is alpha over 2. So if the degree of confidence is 90%, alpha is 10%, and then alpha over 2 is 5% in the two tails. And that's problem number 1. And here's a better picture of what I just drew, with the answers 13.848 and 36.415. Alpha is 1 minus the given degree of confidence, which is 10% in the two tails total. Alpha divided by 2 is 5%, and that's the area in each tail. So this unshaded area is 1 minus alpha, or 1 minus 10%, which is the 90% degree of confidence. And then 5% in each tail. The area above chi-square from the right is 5%, and the area above chi-square from the left is 95%. I like to draw the picture each time, but that's my personal preference. I will show you problem number 2. It says, find the 90% confidence interval for true population variance and true population standard deviation of the ages of seniors at Oak Park College if a sample of 24 students has a standard deviation of 2.3. Notice how it says find the 90% confidence interval for true population variance. It did not say true mean or true population proportion. It said true population variance and true population standard deviation of the ages of seniors at Oak Park College. A sample of size 24 has a standard deviation of 2.3 years. It does not say sample standard deviation, but it is implied to be the standard deviation of this sample of 24. So that is S, 2.3 years. And I will write down what's given. We would like to have the 90% confidence interval for true variance, which is sigma squared, and we want to have the 90% confidence interval for true standard deviation, which is just sigma. We know that we take a sample of 24 students from Oak Park College, and that sample of 24 has a standard deviation S of 2.3 years. And then we're talking about age, and age is normal. And that's all that's basically given in the word problem. Once you know it's for true variance and true standard deviation, it's n minus 1 times s squared over chi squared from the right less than sigma squared less than n minus 1 times s squared all over chi squared from the left. We know our sample size and we know our sample standard deviation. Our sample standard deviation is 2.3. What we have to deal with is finding chi-square from the right and chi-square from the left. And that's what I want to do now. Let's work on the procedure to find those values, and then we'll go back and substitute into this formula. Step number 1 for finding those values, degrees of freedom, is n minus 1, which is 24 minus 1, which is 23. We're going to isolate or block off row 23. Step number 2, you have your picture, your chi-square axis, and you have your chi-square curve, positively skewed, starts at 0, goes to positive infinity. You shade the left tail, and that designates chi-square from the left. Shade the right tail, and on the axis, that's chi-square from the right. Chi-square from the right is larger than chi-square from the left. This unshaded area is our 90% degree of confidence. You could also say that's 1 minus alpha. Alpha is equal to 1 minus our degree of confidence, which is 10%. And that's the area total in each tail, because if this is 90, the two tails have to total 10%, and that's your alpha. And therefore, this is alpha over 2, and this is alpha over 2. And that's going to be 5% and 5%, with a total of 10% with the two tails combined. So 90% and a total of 10% is 100%. That's one of the properties of the chi-square distribution. That's 0.05 and 0.05. The area above chi-square from the right is 0.05, so we'll go to that column first. And then the area above chi-square from the left is 0.95. 0.90 plus 0.05 is 0.95. So isolate row 23 and go to the column that says 5%, which is the alpha over 2, and then for chi-square from the left, go to row 23 and the column that says 95%. And again, this 5% is alpha over 2, and this 95% is 1 minus alpha over 2, or 1 minus 5% is 95%. If the area below chi-square from the left is 5%, then the area above it is 95%. I'm going to break out the chi-square table, and I'm going to isolate row 23 and column 0.05. Your two fingers meet at 35.172. That's chi-square from the right. And then 0.95, the two fingers meet at 13.091. Here are our answers. Chi-square from the left is 13.091. Chi-square from the right is 35.172. And I went to columns 5% and columns 95%. Notice how these columns are symmetrical in the table. So if you're going to column 5% for chi-square from the right, then you're going to column 95% for chi-square from the left. 0.95 plus 0.05 adds up to be 1. That's another way to look at the table. The table is symmetrical. And I'm going to write these two values down. Therefore, on our picture, this answer is 13.091, and this one is 35.172. Therefore, chi-square from the left is 13.091, and chi-square from the right is 35.172. We have those values. So the next step would be to go back and find the confidence interval for true variance and then true standard deviation. Remember, S is 2.3 and sample size is 24. So, n minus 1 times s squared over chi squared from the right less than sigma squared less than n minus 1 times s squared over chi-square from the left. That's going to be 24 minus 1 times 2.3 quantity squared divided by chi-square from the right, which is 35.172. 24 minus 1 times 2.3 quantity squared, I'm just squaring the s, divided by 13.091. Let's find that lower number. (24 minus 1 times 2.3 squared divided by 35.172. 3.459285796. The upper number is 24 minus 1 times 2.3 squared divided by 13.091. 9.294171568. And I'm going to write both of those numbers down. This number, 3.459285796, and then 9.294171568. The rounding rule says to round according to the same number of places as the given sample standard deviation, which was 2.3. So I'm going to round each to the nearest tenth. 3.5 less than sigma squared less than 9.3. Final answer. We are 90% confident that the true population variance falls between 3.5 and 9.3. I can still ask you for the confidence interval width. With a problem like this, the separate questions would be the final answer, the confidence interval width, which is 9.3 minus 3.5, and that's a difference of 5.8. And then I could ask you for the two chi-square values. The next question said to find the 90% confidence interval for true standard deviation, and that's just the square root of the lower and the upper number, and sigma's in the middle. So that formula looks like this. What I highly recommend that you do is not take the square root of 3.5 or the square root of 9.3. You should take the square root of the 3.459285796, the 9.294171568. Take the square root here and not here. So I want to go back and show you that in the calculator. 24 minus 1 times 2.3 squared divided by chi-square from the right, 35.172. And then I'm just going to say second square root of second answer instead of retyping that. And I'm going to write down that number. That is 1.859915535 for the lower. And then the upper, 24 minus 1. And let me start again. 24 minus 1 times 2.3 squared divided by chi-square from the left. And we just received that number a moment ago, but we want to take the square root of that. And let me write down that number for the upper number here. And that is 3.048634378. And now you're allowed to round again to the nearest tenth. Final answer, 1.9 less than sigma less than 3.0. So we're 90% confident that the true population standard deviation falls between 1.9 and 3.0. That difference or confidence interval width is a 1.1. And that completes problem number 2. I would like to show you the lecture notes with this problem. I go through the details, chi-square from the right and left, and we're trying to find the confidence interval for variance and true standard deviation. N is 24, sample sizes, sample standard deviation is 2.3. In order to avoid drawing the picture, the first step is degrees of freedom, so row 23. The column that you go to here for chi-square from the right, you go 1 minus your degree of confidence, which is 10%, the area in both tails. And then each tail has alpha over 2, which is 5%. So for chi-square from the right, go to column 5%. Chi-square from the left is going to be 1 minus alpha over 2, or 1 minus the 5% here, which is 95% above it. So go to column 0.95. And column 0.05 and column 0.95 are symmetrical. And those two columns, if you said column and column, those two columns add up to be 1. Then once you have those two values, and those are the values I just showed you, you go to the table. And this is where I plugged in, and I got 3.5 to 9.3 for the true 90% confidence interval for true population variance. And then I simply took the square root of each side, but I did take the square root of the exact number. I did not take the square root of 3.5 and the square root of 9.3. I took the exact number, and I got 1.9 to 3.0. Again, I can ask you for the final answer. I can ask you for chi-square from the right, chi-square from the left, and I can ask you for the confidence interval width, which is going to be 3 minus 1.9, and that width is 1.1 confidence interval width. I will not ask you for a critical value because there's not one in this section. I just have chi-square from the right and left. I will not ask for E, margin of error. There is not a number we're subtracting and a number we're adding here on each side of the confidence interval. So I cannot ask you for E in this section, and I cannot ask you for a critical value, but I can ask for the chi-square values separately, the right and the left, and confidence interval width. The next problem is the last problem, and it's raw data. A new car dealer is leasing various brand new models for monthly rates in dollars. Estimate true population standard deviation and leasing rates with 90% confidence. Assume the variables normally distributed. This is the same thing as saying find the 90% confidence interval for true population standard deviation. We don't have to do the true variance this time. It's just true standard deviation. And we're going to put the raw data in the calculator. I don't need the sample mean, but I do know I need the sample standard deviation. When you read this problem, it says estimate true population standard deviation, not true population mean, not true population proportion, but true population standard deviation with 90% confidence. So this is a chi-square interval, true population standard deviation. Nowhere in the problem do they mention average or the mean or proportion. So edit, and I'm going to put these under my L2 column, and that's going to be $169, $169, $199, $239, $239, $249. And this is money, so there's a special rounding rule for money. Once you have your values in, you'll go to Stat, Calculate, One Variable Statistics. My information's in L2. frequency list blank and calculate. I don't care about the mean, but I do care about S here, the standard deviation. And we're going to use 36.6. You could use 36.56 because it's money. The raw data values are whole numbers, but it is money. Again, make sure if you don't have a TI-84 that you know how to find standard deviation by hand. And I explore that here in the lecture notes. I'm not going to do that in this integrity video because I've already done that in previous integrity videos. But this is what you would have to do with this raw data, an X column and an X squared column. Plug it into the sample standard deviation formula and you get 36.6. So I'm going to leave it as 36.6 because my raw data values, even though they're money, is whole numbers, and Chapter 3 says to round the standard deviation to the nearest tenth, an additional decimal place. But my final answers here, my lower number and my upper number for my confidence interval, will be rounded to 2 places because of the rounding rule dealing with money. And that's this rule. Problems involving money, final answer. Lower number, upper, rounded 2 decimal places accurately because it's money. And that's the final answer for that. Therefore, let me write down this information and then we will plug into the formula. Again, this problem, we have raw data. And we just found that the standard deviation of this raw data is 36.6. The sample size for this raw data happens to be 6 values. And we want to find the 90% confidence interval for true population standard deviation. And when we hear those words or see those words, we should think square root of n minus 1 times s squared divided by chi-square from the right, less than sigma, less than square root of n minus 1 times s squared divided by chi-square from the left. The hardest thing to find next would be to find the 2 chi-square values from the table. So we would go to degrees of freedom, n minus 1, which is 6 minus 1, so isolate row 5. And then I'm again going to draw the picture to find my 2 columns, but you can avoid that if you like the procedure. 0 to positive infinity, positively skewed, shade the right tail, that's chi-square from the right on the axis, and shade the left tail. That's chi-square from the left. I do realize that these lecture notes all involve 90%. It doesn't always have to be 95%. And in class, I cover a couple of examples where it's not 90% confidence. But again, this is 0.90, or 1 minus alpha, because alpha is 1 minus 0.90, or 10% in each tail. So alpha is 10% since our given degree of confidence is 90%. And this unshaded area between these 2 chi-square values is the degree of confidence, 90%. 1 minus 10% is 90%. Alpha is 10%. This is alpha over 2, which is 10% divided by 2, which is 0.005. And this is alpha over 2, which is 10% divided by 2, which is 0.05. So 5%, 90%, and 5% is 100%. The area above chi-square from the right is alpha over 2, which is the 10% divided by 2, half of 10%. And the area above chi-square from the left is 95%, or 1 minus alpha over 2, which is 1 minus my 5%. It's 95%. So these are the two columns that I'll go to. And then row 5. Chi-square table. Row 5 with the left finger, and I can really enlarge this here. 0.05 with the right finger, and that's 11.071 for chi-square from the right. And then 95% column, that's going to give us chi-square from the left, 1.145. So these would be my two values, chi-square from the left, chi-square from the right. I went to column 5% and column 95% and row 5. My sample size was 6, but go to row 5. And I'll write these down on the axis. Once you have these, you got it made. 11.071, 1.145. And now we'll go back to our formula. And I'll write those here. Chi-square from the left is 1.145. Chi-square from the right is 11.071. Here's the formula. This is going to be the square root of 6 minus 1 times 36.6 quantity squared, S squared, divided by 11.071. Square root of 6 minus 1 times 36.6 quantity squared divided by 1.145. And I'll show you how to receive both of those numbers. Let's work with the lower number first. 6 minus 1 times 36.6 quantity squared divided by chi-square from the right, 11.071. And then I need to take the square root of that quotient. And I do second square root of second answer. 24.59646.315. I want to write that down. Before I take the square root, I got 604.9859995. And then I got 24.59646.315. Now, the upper number, that's going to be 6 minus 1 times 36.6 squared divided by chi-square from the left. And that number under the radical is 5849.606987. And then we take its square root. So the square root of second answer. And I'll write down that number, 76.48272345. Since this is money, our final answer for this confidence interval for the true population standard deviation, 90% confident, is going to be $24.60, less than sigma, less than $76.48, because it is money. And that is the solution to problem 3. Again, if you missed any of the details are in the lecture notes. And in class, I'll be showing you these types of intervals with something other than 90%, I promise. So that you can see how, in another situation other than 90, to find chi-square from the right and chi-square from the left. And just so you'll see the rest of the lecture notes, have chi-square from the right and left, and the procedure again without having to draw the picture. And then if you need this, I actually plug into the formula. And these are the numbers before I take the square root. And then once you take the square root, so $24.60 to $76.48. The confidence interval width would be $76.48. minus $24.60. And that width, confidence interval width, would be $51.88 if I ask you for the width. And you just subtract the upper minus the smaller. $51.88 is the confidence interval width. The last video that I will show you, and that's not on this video, will be the practice test for this chapter 7. At this point, you should be able to do all of the worksheets and the practice test, but I do plan to record the practice test for those of you that find it helpful. And again, I'll show you how to do the problems by hand and calculator. But do remember, the TI-84 does not do this for you. The only thing it's useful for is finding S if it is a raw data problem, the sample standard deviation. Hope you have enjoyed the video. This is probably one of the more difficult sections in this particular chapter. The hardest part is finding these values from the table. But once again, don't forget the properties of the standard normal distribution in Z, the student t distribution in T, and now the chi-square distribution in variable chi-square. Know the properties of every single distribution and how the table works. And then this, finding these two values, after you find these, the formula is really not that bad for finding your final answer. Stay tuned. The practice test will be posted very, very soon. God bless you.